and then be like, I got it wrong. You saw something that probably looked like this, dx dt squared, and then what do you add to it?
dy dt
squared, and it's the... So that's the speed of the particle at any given time. So you could write the general speed function, right? So for 11, it says find the speed of the given motion of a particle. Find any times where the particle comes to a stop. So if x is equal to t squared, you've done things like this all the time. What's dx equal to? Or what's dx equal to? 2t. I can almost write. I caught it. I see it. 2t dt, right? So what does dx dt equal?
2t over t squared.
This is just 2t?
All right.
It's just 2t, right? Right? I think so, right? Okay, so if y is equal to, was it t cubed?
Right.
Is that correct?
Right.
I know. I'm having trouble like writing things today. What's dy dt?
3t.
3t squared dt, right? So dy dt is equal to 3t squared. So the formula, the speed at time t, is going to be equal to 2t squared plus 3t squared square rooted, right?
I think it's 3t squared.
Sure.
I really feel like I'm at a disadvantage of not being able to speak Chinese.
Not only in this classroom is that true. Not only in this classroom, but globally. I recommend it. If you want to learn 2 languages for global importance in the next, I don't know, your lifespan, learn Mandarin and Classical Arabic. Those are the 2 right there. If you want to be marketable and get a job. Have you seen how big the Chinese charter school has gotten? How do you figure out when it comes to a stop? What's the speed of a particle when it stops?
Zero.
It's 0, right? So what do you have here? 0 equals that thing, right? Is there any time when the speed is going to be equal to 0 when it stopped? Yeah, t equals 0. So this particle is not moving at time equals 0. At time index 0. When you plug in 0 into that, what do you get?
0.
Does that make sense? Theoretically, could you have something else in terms of t and something else in terms of t that makes this more interesting? Yes. Yes. You absolutely could, and therefore it becomes more interesting when you do other ones like that. Okay. Representation of the actual function. It's just a general, here's a path, right? How many times in your life have you found the equation for a tangent line? Just curious. How many times do you think? Like a billion? Like all of them? And then like, it's like, if you ever lost on the AP exam, what do? Take the derivative of the function, set it equal to 0, okay? Like, that might help you. There's your tangent line. It's asking you for the equation of a tangent line. How many pieces of information do you need to write the equation of a line? You need 2, and slope and a point would be great, right? If you have 2 points, what do you also get? Slope. But your goal, your immediate goal whenever you're asked to write the equation of a line, you want the slope, and you also want a point. Okay, so let's look at 11 right here. Time equals what? 2. Can you tell me where the particle is at time equals 2? What is it at? 4 what? Almost. 4, 8. Okay, hey, so do we have the point? Yay, we have the point. We're halfway there. All we did was plug in the time into the parametric equation. How many different ways can you state what slope is? How many different ways can you state what it is? I'll give you one of them. So stop there. I can't tell you how many times I've seen really, really brilliant students get to here, do all the calculus right, and then make some like really small algebraic mistake. It's not you. It's just human nature. You're not looking for it. So you're like 8 plus 8 is 12. And you're like, that is not right. Okay. Talk about this picture right here. So here's the origin right here. This looks like a lot, but it's really not that bad. How do you pronounce this? X with this 0? Anybody? Not. X naught. I mean, like 0 as the initial. So the idea is X naught, Y naught is your starting position. AB. What do you think AB are? What do you think AB are? So what do you ID? Yeah. Who said it? No, that was really good harmony right there. Someone said one part and someone said the other. What can you use A and B to find?
0.
The what? The slope. How far over do you go from this point to this point?
B.
A. How far over do you go here?
A.
How far over do you go here?
A.
So the distance between each of these points is A horizontally, but what about the y, the vertical? B horizontally, right? So each time you go from point to point, I'll cut to the chase. What's the slope of that line?
B over A.
B over A, exactly. So how do you go about writing the equation, the parametric equation of a line? X in terms of t, you okay? Y in terms of t. With these two pictures here, you have to pick an initial point. What's your initial point? X naught and Y naught. And then you have to know where you are. Every time t increases by 1, how far over did this go in the x direction?
A. 1.
And for y, what's this going to be? bt. This is what it looks like when you write the equation of a line in parametric form. Now here's the thing. What did we say about path? So look, for example, ready? When time equals 0 here, what happens to these terms? They go away. Meaning, where are you? X naught. Oh, look, you're at. Oh, okay. You're taking it in? Okay, so here are a few other things to understand. Theoretically, where could my initial point be? Anywhere you want. Anywhere you want, right? So theoretically, could I pick my x naught, y naught to be like literally this point? The only thing that would change is where you are on the line. If I drive a car on the road over there and then I drive it differently, they drove on the same path, but they drove the path itself differently. I could start somewhere and go forward and backward and forward and backward, but it's the same road, right? Same thing here. We've already talked about this. How many different ways can you parametricize an equation? An infinite number. But the point is, the general form is you just have to pick an initial point, which is any point on the actual equation, right? And then you need to know what the slope is, effectively, what direction you want to go in. So if you know dx dt and dy dt, you can write the equation here, right? Do we know those things? Look, we did so much more than we needed to do on this, right? We know what dx dt is, right? What's dx dt? 2t. So what is dx dt when t is equal, was it 2? 4. What's dy dt when t is equal to 2? It was 12, right? So what's the equation going to be? Well, what did I say you have to find first? Oh, your starting position. Well, what does it say for this one? When tangent is t equals 2, right? Do we know where we are when t equals 2? When t equals 2, you're at what, 4, 8? So you go down here and you say, okay, it's going to be 4 and 8. And what do you add to these? 4t and 12t. Exactly. It gave us an anchor point. It gave us a specific time. That time gives us where we are on the road at a specific instant. What do you need to write a line before? You needed a point and a slope, right? So you effectively need the same thing. You need a point somewhere, something that's on. Oh, do you already have 2 of them? You have one right here, for example, right? And then you need a slope. You need a slope. Okay, so theoretically, could you find the slope between these 2 points? Yeah, 5 minus -1 over -1 what? Minus 2. So what do you end up with? You end up with 6 over -3, which is -2. And then you're like, wait a minute. What was that general form? xt is equal to what? X naught plus at, and y in terms of t is y naught plus bt. Oh, but wait a minute. What did we say slope was equal to in parametric land?
B over A.
It's b over a, right? So theoretically, if we wanted to use this as our initial point, that as our x naught, y naught, like that, we could write now xt is equal to 2 plus -3t. Careful. This is -2 over 1, right?
Oh.
So what's b going to be? What should b be?
-2.
So that's b and that's a. So a is going to be, what in this case, what's a going to be? 1. So 2 plus t. And y of t is going to be what? -1 minus 2t. Now we have something we think is an answer, right? We think it's an answer. What's a great thing to do that I'm really trying to get all my students to do when they have time? What should they do? Check your answer. Well, is this a line? How do we know if this is a line in parametric land? it fits the form, right? Does it fit the form of a line? Yes, it is a line, right? So the only qualification is now, does it go through those 2 points? How do you know if this line goes through these 2 points? Well, okay, be specific. Plug in what t values?
0 and 1.
So we built this. If this is our initial point, this is where this should be true when t equals 0, right? Let's plug in t equals 0. What happens? 2 and? Okay, so it definitely goes through that point. How do we tell if it goes through this point? How do we tell if it goes through that point? Okay, so it's chugging along on the line. It gets to -1 when t is -3. So where should we take this -3? We plug it in right here. What's -1 minus -2 times -3? What would happen if it didn't go through that point? We plug in -3 and we get like 7. It wouldn't be there at the right time. It wouldn't be at the y coordinate at the right time. It'd be a contradiction. So we know this works because, so another way to think about it would be this. We also know, you could just do it like this. We know that -1 minus 2t has to be equal to 5. -2t equals, so t equals. So the particle has an x coordinate and a y coordinate that we want at the same time. So that means it's at the point at the right time. So does this line go through both points? Yes, it absolutely does. Now the question is, how would we go about speeding up or slowing down this particle on the line? How could we make it so it travels on this? What could you do? What? By what? Yes, by the same factor. Exactly. So right now, we have 1 and -2, right? We can make it 1 billion and -2 billion. Is it still going to go through the same points? Yeah, it's still going to go through the same points, but it's going to get there a lot faster. Does that make sense, everybody? So what you're going to do sometimes, I'm just prepping you for this. You're going to get questions that are going to be like, find a parametric equation for a line that goes from this point to this point. It starts here at time equals 0 and gets here at time equals 5. So you have to find the equation, and then you have to speed up or slow down the particle so it's at the right place at the right time. Is that kind of sinking in there a little bit?
Well, that makes so much sense.
Kinda. It's weird. It is weird. Okay, so before we do another one, let's just take a look at this. We talked about this earlier, accidentally, because I misread the question and got really excited. I was really excited about this. Apparently a lot. Okay, so that was Pythagorean Theorem. Yeah, Pythagorean. Anybody prove the Pythagorean Theorem in this class? Yeah, it's considered the most proven theorem in the history of math because many different cultures that were independent of one another came up with their own proofs. So there was like a Chinese proof, there's an Italian proof, there were lots of different proofs, and then have there been many more found? Absolutely. It's kind of what's the right word I'm looking for? It's relatively unfair that we call it what? Pythagorean Theorem, because in terms of like who thought of it first, he was like 2,000 years after like the Chinese and the Greeks figured it out. Pythagoras was Greek, sorry. So like the Chinese definitely did it like 1,500 years before he did, or something like that. But did they know each other at that time? No, it happens. Sorry. What? Just like soccer? Is it a Chinese game?
Yeah.
Oh, I did not know.
Really?
I don't really.
Yeah, we had that conversation.
Really?
Yeah.
I learned something new.
Korean.
Is soccer like? Is it important in the world? Do people like care about soccer?
I love
Sorry, I don't know soccer.
Here we go.
Interesting, actually, I don't know soccer. I only know
Let's not play this game. Okay, we're gonna stop playing this game. It's not gonna go good places. Okay, a particle moves along a curve in the XY plane. Okay, we finally get to do something a little nicer. Oh, it's a little more entertaining, right?
Yeah.
Where t is time. Find the velocity vector and the speed of the particle with t equals 1. Go. For reals. At least they're getting more creative. Exactly. It's very hard to understand it. Yeah, that's really good. Cameron, the way you say my, or his, or her, or yours, so like you is me, I am 我, he, her, there's no gender difference, ha, right? Right. To make it possessive, you put a de after it, so like 你的, 我的, 他的, right? So it's like 我的. They're making fun. Okay, I can translate. They're making fun of my tones. I messed them up, and it means like donkey all of a sudden. Like 他的 means like his name, right? 我的 means my name. 你的 means your name, right? So when I was when I was very small, in my first Chinese class, we had to write little papers with paragraphs. So we had to write a story, right? So I read my story, but the title of my story was My Day. So 天 is day, right? So my title, I go, 你好，我叫是周五，我的天, you know? But the thing is, 我的天 doesn't mean my day, it means my God, right? So I'm like, my God, first I ate breakfast, you know? So you say 我的一天, right? No, you say 我的一天, right? Yeah, you say, so you say my one day, right? So believe me, I messed up like that all the time. I also still have a really, really, not negative, but every time I hear my Chinese name, I get really anxious immediately, because the only time I generally heard my Chinese name was 我的中文老师, my Chinese teacher, saying 是周五, like, you know, like, only when my Chinese teacher was like calling me up to say something, right? So anytime I hear my Chinese name, I'm like, okay.
What is your
So,
Chinese name?
oh, and by the way, that was all recorded on tape. I'm totally not taking that out, by the way, because that was good material. That was great. We didn't specifically do this, but what's the great format for vectors? You've seen things that look like this, right? For vectors. So what? Oh, yeah. So you're looking for dx dt and dy dt. How many of you have taken physics before? You've seen a vector before. This ain't brand new, hopefully. So what's dx dt? What's dx dt? Ah, sorry. 2 plus e to the t. And what's dy dt? 3. It's kind of a cool, at that moment, it has nothing to do with t. Well, it's really cool. The vertical change has nothing to do with the time. It's just always going to be 3 because it's kind of like a linear rate of change just for y. Okay, so that right there is the velocity. How do you find the speed? Ah, so this is the velocity, right? No, so you can do it. What I would like you to do is square it and then plug t in, or you could plug t in and square it. You can do either way you want. Oh, does it say velocity when t equals 1? So yeah, so v of 1 is going to be what? 2 plus e, comma, 3. So the way speed is just the what? What did I write there? What does that mean, those bars? Absolute value, which is the speed at 1, right? Speed at 1 is the magnitude of velocity, right? So what do you do when you do magnitude? It's a scalar, right? It's a single number. So what's that going to be? It's going to be the square root of 2 plus e squared plus 9. Done. There's your speed. Speed is scalar. It's a number. And it's always what? Positive or 0. Ling. Now, does it say what form the line needs to be in? No. So most of you assume that you want to do it in maybe non-parametric form, which is fine. Either way is fine. Either way is fine. But hold on. I like a lot of what I'm seeing right here. So let's write down what we know so far. Well, you could know dx dt. What's dx dt?
3t squared.
3t squared. And what's dy dt? What's dy dt? 2. Okay. Someone asked, well, we don't know what the time is. They actually did tell you what the time was because they told you that that point passes through that equation, that function passes through the point 1, 2, correct? It passes through the point 1, 2. So 1 needs to be equal to t cubed, and also 2 needs to be equal to what? 2t. Well, if that's true, what does t equal in this case? So t better equal 1, but over here, what do you get? Oh, what's time equal? What happens? I have a question. What happens if we did this but we got a different time? Hold on, Cameron, do the blame thing later, okay? Mom, Dad, don't fight, okay? Oh, you're just taking up for yourself. Okay, I got it. Okay. What would it mean if you had different times? You said it.
Not gonna work.
It won't pass through that point. So when you do this, you better get the same time. If you don't, check your algebra. Okay? Or it would just be a bad question. It would be like saying, like, here's the equation of a line. Here's a point that's not on the line by the tangent. It wouldn't make any sense, right? Oh, but do we have the time now? We do. So what's dx dt when time equals 1? 3. What's dy dt when time equals 1? 2. So therefore, what's the slope of this line? 2/3. Do we have a point? Do we have a slope? So y minus 2 is equal to 2/3 times x minus 1. Do people agree with this? Oh, you do. Nice. What I like, what I'm telling you, though, you did the parametrization. See this right here? It's not that this is wrong. It's just that you can get better than that because, look, what's t equal? 1. So theoretically, 1 plus 2/3 t, 2 plus 2/3 t. Maybe, I think that's right. Okay. Let's try another one. Let's learn by doing today. Hold on. Then I just want to show. How about this? The reason I want to show you is so that when the epiphany strikes you on your homework, you never use it. Okay? So I'm taking it away from you. So you're looking for something that looks like this, right? Any ideas about? Oh well, you know what? I'm not. You know what? I'm going to let you guys find it. So the real question, we looked at a circle, right? And do you remember how we got the circle? It was x of t is equal to what? Sine of t. Oh, so I think we did cosine for this one. Does it matter which?
Yeah.
Not really. It just changes where it starts. And y of t was what? Sine t. Do you remember that, everybody? We did this. We made a table, and what did it generate for us? A circle, right? So that should probably give you an indication of what type of functions we're going to need to make one little change here. Is this a circle? No. Is it similar to a circle? It's similar to a circle. So here's a question for you. When we did this for circle land, we graphed it by using a table, right? And it really looked like a circle, so we're like, oh, it must be a circle, right? How do we prove it's actually a circle? Any thoughts? Basically, I'm asking you, another way to say this would be x squared is equal to what? Cosine squared t, and y squared is equal to? And then you can add them, and what do you get? X squared plus y squared is equal to cosine squared t plus sine squared t, which is what? So x squared plus y squared is equal to 1. Oh, so we just proved it's a circle of radius 1. So let's look at this one here for a second. We squared it, we did this, and it turned into this. We're looking to do the opposite and end up, but not start here, we're changing just a little bit about it. So do you see how it's similar? It might not pop into your head, which is fine, but you see how it's really similar, right? Does anybody have an idea? Okay, go ahead. What? why is it legal to square it? I'll put a pin in it and come back with a good answer later, other than it's equal. Just go with that for now.
What is equal?
X is cosine t. That's it. X is cosine t. Okay. So the question is what? We're not done, but you gave us the hint. This is 2x squared plus y squared is equal to 1. That is 2x squared plus y squared is equal to 1, correct? So how about we let x equal 1/2 cosine t and y equal sine t. Does that work? You can actually see it right there without doing any algebra, because what happens if you throw x equals 1/2 cosine t into there? Oh, but it's a cosine goes away, right? What happens when you throw sine into there? Oh, so you have cosine plus, oh, is that true? It doesn't matter what you choose, it is true, right? Now the other thing I could do is do this. I could not give you this. And I could say, what is that? How would you go about figuring that out? Let's say you just started with this. I could give you this. If you just started with that, how would you try to prove what that equals? What would you do? Yep. So you do x squared equals 1/4 cosine squared t, and y squared is equal to what? Sine squared t. And then you do one more thing times 4. So you have 4x squared is equal to cosine squared t. And then you take these two things and what do you do? What do you do with those two equations? You add them together and you end up with 4x squared plus y squared is equal to 1. So that's how you could prove what it is without knowing. So there's lots of different ways I can effectively ask the same type of question. I could start you with this and ask what the parametric form is. You could start with the parametric and go to here. You have to be able to do both directions. Does that make sense, everybody? Infamous. So you could come up with different answers. Find me one of them. When you think you found one, raise your hand and I'll tell you. Just find one. Okay, you guys need help apparently. Y is equal to x squared. Sorry, not x squared. X, right? X times x squared minus 1. So y is equal to x times
0,
x plus 1 times x minus 1. So how many intercepts does it have? Here, here, and here.
It stays on the
Yes, it stays on the curve, but that question is asking you in which direction are we moving? Is it going from left to right or is it going from right to left? Literally, how do you figure that out? Plug in, how many points do you need? You need a direction, right? It's going to go in one direction or the other. So look, what do you have here? Plug in time equals 0. Where are you? 0, right? Plug in time equals 1. Where are you? 1, 0. So at this point right here, at this point, let me get a different color here, sorry. At that point right there, what's the time? That's time equals 0. What point is this right there? Time equals 1. What point is that right there? Time equals what? Negative 1. Exactly. Can time be negative? Yeah. It's just an index. It's kind of inaccurate for us to ever call it time. It's an index. So it's a minute ago. Like, where was the car? You know, you can rephrase your question to make sense. Last question I have for you is, we have talked about this right here. Do you know where this comes from? I gave you the geometric representation of it, right? Remember I gave you the geometric representation? dy dx is equal to dy dt over dx dt, the slope of 1. We just did that at the beginning of class. Do you know where, like, why is that true by more than just a geometric proof? It's not really a proof if it's geometric sometimes.